Vacation. I'm a stand-up comic, and today it's NASA Universe Unplugged live chat. And today we're going to talk about exoplanets. One of the things NASA looks for is whether a planet is located in the habitable zone around a star. So why is that so important? Check out this video to learn a little bit more. And then we'll come back and take your questions.
Habitable zone?
Let's see if the telescopes can find any Earth-sized planets around here. I said I'm working. I'm looking here.
Like those?
I'm trying. Well, what do you know? Planets. Everything here's all bunched up around that star. There's a large planet right next to it over there. A couple more further out.
And one right smack in the middle of the habitable zone.
Hang on then. Taking us in.
So, if this one turns out.
So that was from the habitable zone, and we learned a little bit more. It was also from The Expanse. That was Kaz Anvar from The Expanse, I believe. I'm here with two NASA scientists, and you're going to get to talk to them, but let me introduce them. We have Tiffany Kataria, is that correct?
Kataria, that's
yes,
one.
Good. Okay. It's a planetary scientist at NASA's Jet Propulsion Laboratory whose research focuses on the atmospheric structure and dynamics of exoplanets, ranging in size from Jupiter-sized to Earth-sized planets. And then on your lower right would be Robert Hurt. He is an astronomer at NASA's Spitzer Science Center who specializes in visualizations of scientific observations and who wrote and directed the Habitable Zone episodes for the Universe Unplugged. You guys, I'm a comic. What is an exoplanet? Sorry.
No, that's fine. I'll take that one. So an exoplanet is a planet orbiting another star, like Earth orbits our sun, and the other solar system planets exist in our solar system. So exoplanet scientists so far have discovered over 4,000 exoplanets, and so these are ranging in size from Earth to from Mercury to even larger than Jupiter. So a wide diversity of planets that have been discovered so far by various techniques, which I can also talk about.
Okay, and so yeah. Robert, tell me, what exactly is this habitable zone that the show is named after?
Well, the habitable zone is one of the observable things that we can pick up when we look for exoplanets around other stars. It's basically, one way you could define it is if you were to put Earth around a star, a different star, how far could it be away from that star and still maintain liquid oceans on its surface? So if we can find exoplanets orbiting a star, we can figure out how far away they are from the star. And from observing the star, we can figure out how large it is, how hot it is, and how much light and heat it puts out. We can actually calculate sort of a range of distances that would be consistent with having the liquid water potentially existing on its surface. Now, it's absolutely no guarantee that there's going to be liquid water, and it's certainly no guarantee that the planet's actually habitable. But that was one of the things that we wanted to do with the Habitable Zone videos, is sort of let you travel along with some fictional space explorers, finding planets that are in the habitable zone, and find out all the different things you have to worry about other than just where the planet is located.
And can I ask, how do you find exoplanets?
Yeah, I can take that one. So there are many different ways to find exoplanets, a lot of which, at least recently, you actually are staring at a star and inferring that a planet is there, so it's somewhat of an indirect detection. So one of those is called the transit technique, and so a lot of you may have heard about that, given the Kepler Space Telescope and now the Transiting Exoplanet Survey Satellite, TESS, which uses the transit technique to find exoplanets. And so the basic idea is that you're staring at a star, and if there's a planet passing in front of that star, you should see the starlight dimming as a function of that planet transiting in front of the star. And so a bigger planet will block out more light, a smaller planet will block out less light. And so then using those measurements, we actually have a estimate of the planet's size, and so we know if it's something more like an Earth or something like a Jupiter. But there are other techniques to find exoplanets, like the radial velocity technique or the wobble technique, and so this uses the gravitational tug between the star and the planet to infer that a planet is there. So a more massive
and that's
planet
what the
Oh, go ahead.
And
Yeah.
that's what the transit method is? The transit method
No,
is
no.
that
So
gravitational? Oh,
no, so the transit method will measure the size of the planet, and then the radial velocity technique, I would actually say, is a complementary technique, because from that measurement you actually get the planet's mass. And so with a mass and a radius, you have a planet's density. So then you know if the planet is more rocky, like an Earth, or something that's more like a gas giant, like Jupiter. But ultimately, what we
okay.
want to do is take pictures of these planets, actually images of the system. So that's a technique called direct imaging. But we've only been able to do that for the most massive, the most giant planets so far, because it's a real challenge for the essentially to block out the starlight so that you can see a planet there.
How many pictures of
And of
that
course,
have they figured out? Just quick question. Yeah,
Sure.
how many?
Yeah. So whereas for transits and radial velocity, we've been able to find on the order of thousands of planets. For direct imaging, so far we've only really been able to do it for tens of planets. But there are scientists and engineers working really hard to essentially work at getting at the angle you need between the star and the planet to really find. So ultimately, you want to find an Earth-sized planet in the habitable zone of a solar-type star, because that's what we understand in the search for life. And so there are lots of engineers and scientists, really smart engineers and scientists, working on figuring out the best ways to image those sorts of systems.
Okay, and Robert, did you have something you wanted to add?
It's worth noting also that for the direct imaging, you're looking at planets that are so far away from their star that they are like proportionally well beyond, say, Pluto's orbit. So it's radically different. It's very, very different than the kind of terrestrial environments we would be interested in, particularly in the search for life. So that's why we rely on these other indirect methods like the transit method, because they're much better at finding planets that are closer to the star than direct imaging currently.
Okay, and we have our first question from the internet, you guys. It's at Dr._eclectic asks on Twitter, do we miss the vast majority of planets that can't be detected if their transit is not aligned between the parent star and our Earth? It sounds like Dr. Eclectic knows what they're talking about in that question, because those are many words.
Yeah.
Who wants that one?
I'll take that one. So yeah, I mean, I guess so. Given a single detection method, such as the transit method, you would run the risk of actually missing out on a lot of planets, because you also have to find planets that essentially will transit along the star, and so it needs to be in a favorable inclination relative to the star. And it's also harder when the planet is smaller. So that's actually so ultimately it's a relative measurement between the star and the planet to actually detect the transit happening. So essentially this actually ties very well into the habitable zone. One of the reasons we look at M dwarfs specifically for planets in the habitable zone is because they're much smaller than our sun, and therefore the transit ratio between the star and the planet is actually much larger. So it's much easier to find a small planet around a smaller star than it is to find a small planet around a bigger star. And so that's what Dr.
Because it gets lost.
Yeah, well, it's just a smaller signal that you have to search for. And so it's very challenging to do that. And so that's why M dwarfs, and also additionally to that, the habitable zone, this Goldilocks zone for M dwarfs is much closer into the star than it is to our sun. And that's also what the video shows you. And so given that, closer into the star means that it's more likely to transit and we're more likely to see it. So those kind of two coupled properties make transits much easier to look for, habitable planets to look for around M dwarfs. But that's why complementary techniques are so important. So that's transits, but using all of these other techniques, radial velocity, direct imaging, and other things that I haven't even mentioned, makes it, gives us a better chance of having a more complete sample. Yeah, Robert, you wanted to add something?
Yeah, just to add that, just to kind of close on Dr. Eclectic's question, is that, every time we do detect one of these systems that has a transit, we know statistically there are many, many more that we didn't see because they weren't oriented in the right direction. So really, we're just getting kind of the tip of the iceberg on exoplanet detections, and we know there's so many more out there. But until we get a chance to take a spaceship and fly to some of those, it's going to be really difficult to detect the planets in some of those others that aren't aligned well.
Here's my question. So is an M dwarf like an M class in Star Trek? What is an M dwarf? Hi, we'd like to just peel it back. Let's start real low, because this one. What's an M dwarf?
in Star Trek, an M-class planet is a place like Earth. It's very habitable. But M dwarfs are actually really, really different. They are the smallest stars you can have that are still stars. They start around about 100 times the mass of Jupiter. And basically, if they were any smaller, they wouldn't have enough pressure internally to maintain nuclear fusion going on in their cores. But they're also really interesting because they are the most common stars. There are far, far more M dwarfs out there than there are suns, like G-type stars, like our own sun. So they're very common, but they're very faint and they're very small. M dwarf stars themselves are only about the size of Jupiter. Basically, imagine the Jupiter system as like its own solar system. That's the kind of things that we're looking at when we study planets around M dwarfs.
Okay, so that is very small. Now, you should know that Noel James on Twitter has a couple of questions. What are the main aspects required to declare an exoplanet habitable?
So it sort of actually depends on who you ask, really. I'd say, sort of classically, I think Robert may have already touched upon this a little bit, the temperature being a main driver. So we want to search for a planet that might share the same insolation, the same radiation that Earth receives. And so that's sort of why we make these comparisons between M dwarfs and solar type stars in terms of where their Goldilocks zones are. Habitable by whom or what, indeed. But another aspect may very well be things like the composition. So in the earlier version of the earlier episode, I should say, of the habitable zone, they touched upon this as well. So you want the right gas mixture in your atmosphere. So that's the job of telescopes, to search for those gases in these planetary atmospheres. So things like water or carbon dioxide or methane or ozone, these are fundamental gases we see in our own atmosphere that we think would be important for the processes of life to evolve on another planet.
And those are detectable by telescopes now? You can detect the type of gas with a telescope that we currently are using?
Yes and no. So I guess the gases themselves are detectable, but the measurements themselves are very challenging, given that these are very small signals to detect out of a planetary atmosphere. And so with the transit technique, for example, you're looking at information from the star and essentially subtracting out all of the stellar information, and then you're left with information about the planet. And so that's a fraction of the signal that you get from the star. And so that's why techniques like direct imaging would be so favorable, because you basically don't even worry about the signal that you're blocking out the signal from the star to begin with before you're extracting information from the planet. It's independent of one another, essentially.
Okay. And now,
so sorry, just to close that in terms of the molecules themselves, things like water have been detected, but just not on planets that are potentially habitable. So on these hot Jupiters, these Jupiter-sized exoplanets that are really close into their host stars, we found water in dozens of those planets. So the molecules are detectable, but so far just for kind of favorable planets that are more favorable given the current telescopes we have online. But scientists and engineers are thinking about the next generation of telescopes that may be able to more readily detect these molecules.
Okay, and when you say habitable, ideally it's habitable eventually by humanity, because we wish to go to space. But but what about now? Like, are you just looking for any kind of life, Robert? I don't know, Tiffany.
No,
sure.
Yeah. No. Go ahead, Robert.
Yeah. At this point, I think any astronomer in the world would be overjoyed to detect the slightest evidence of the smallest bacterium existing independently somewhere else in the universe, right? Obviously we know that life is possible because we're here. So the universe certainly allows life to exist. The one thing that we don't know from a sample size of 1 is how frequent is it? Is this a 1 in 100 kind of odds? Is it 1 in 1,000? Right. Is it 1 in 1,000,000,000,000? And so our search for life, not only in around exoplanets, but even search for life in the solar system, the possibility that might have popped up on Mars or other planets or in the oceans of Europa, if we can find independent evidence of the chemicals, the processes of life coming together independently in more than one location, that actually gives us an idea that it might be a simpler and more common kind of thing. On the other hand, if it's even if you have a nice ocean-covered planet and nice tides and summery conditions, if then it still only happens 1 in a million times, then life might be very, very rare in the universe.
Okay. Now we have another question. This is from Facebook. Is how many of the over 4,000 exoplanets, 4,043 exoplanets discovered, are located within the Goldilocks zone, and why Goldilocks? What's happening? Okay.
Homework question.
Yes, please. So the Goldilocks zone sounds like this might be something that she's looking for the perfect bed, I assume. That's what it's the Goldilocks story. So what is the Goldilocks zone, and how many of those planets are located within that zone? Who wants that one? You want to start, Tiffany?
Sure, I can take that one at least to start. So the Goldilocks zone is based off of the story of Goldilocks, getting the porridge either too hot or too cold, and so the same idea applies here in finding planets that are just the right temperature to harbor life, to have this liquid water on their surface. And so this is what the habitable zone is really defined as. So of those 4,000 or some odd exoplanets that have been discovered so far, roughly about 50 of those or so, I would say, are potentially habitable based off of this kind of temperature argument. So these are the planets that are the right size and the right distance from their particular host star that suggests that there might be liquid water on their surface. Of course, we don't know that answer for sure, but these are the best candidates to go out and search for those molecules and other properties that might suggest life is there.
One thing that I just find so interesting is that out of these over 4,000 planets now, we still haven't found a single one that's a good direct analog to the Earth. Speaking of, the same size as Earth, at the same distance from a star very similar to the Sun. That is still, as many Goldilocks planets as we found, right? That's still not a direct parallel we found. So that kind of speaks to just how rare and special I think Earths are.
And I think it also speaks to the current, time for which we've been actually searching for these planets, because one of the challenges with transits is that you actually want to observe the system transit a bunch of times so that you can confirm that it's orbiting that particular star. And so for an Earth-sized planet orbiting a sun-like star, given its orbital period of a year, you'd want to observe it for 3 or 4 years to actually confirm that it's there. And so given that it's a small signal and you really want to verify that that planet is there, I think that also just points to how much more time we need and better techniques to maybe image those things instead of
right. Because are we sort of in the first year of finding these?
Oh, no.
Have there been cycles? No. Okay. I don't know. How many have we seen cycles?
Yeah. So people have been searching for exoplanets, in the broadest sense for decades. And so the first detections were actually made in the early 90s. But those were for planets that are larger on the whole and using a wide range of techniques. But, in terms of these small planets, the potentially, rocky, potentially habitable planets, I would say a lot more forward progress has been made on that within the past, 10 years, 5 to 10 years.
Okay.
I think
we've seen several cycles.
Yeah. Right.
So
potentially. Yeah. So Kepler and TESS have been, operating or have really amplified our number of discoveries thanks to these surveys, given that they're staring at either the whole sky or patches of sky for planets.
Okay. We do have another question that goes very much to the basics, so I, of course, enjoy this question. Brody, with a bunch of numbers, 889-58302, hike. He would like to know, how do suns form? And then he gets a little snarky, like, I'm going to believe a bunch of stuff smashed together and started to burn. So how do suns form is the real question Brady has.
Well,
Robert.
A lot of stuff did kind of smash together and start to burn, but not burn like fires, not like on Earth. But no, the amazing thing is that when you look out through the galaxy, you see, you look up the night sky, you see lots of stars, and you think that's what the galaxy is made of is stars. But actually, there's a lot more out there. The space between stars is actually filled with gas. It's mostly hydrogen and helium, little traces of other elements mixed in. But the gas that's flowing around the galaxy, it's not smooth and uniform. It has eddies and currents and places it clumps together and builds up. There are basically, you can think of it almost like stellar or gaseous traffic jams that occur in the galaxy, where a little overdensity occurs. It's like driving down the 405 freeway. If someone like slams on the brake once, then a bunch of cars pile up behind them, and more cars pile up behind them, and it ends up creating a jam that lasts for hours. This kind of thing happens in the galaxy too.
Yes.
Sorry, I didn't mean to give you a trigger warning event there, but you know, so in the 405 when that happens, sometimes the cars smash together and you get a pile up of rubble. But in these interstellar gas clouds, sometimes what happens is when enough of that material starts bunching up, the gravity of everything distributed through that gas starts to actually take hold and pull it together even more. And you get these regions where the density of the gas goes way, way up. And in some areas, if it gets high enough, and from the turbulent motions and things start swirling around and piling up, you get certain regions where the overall density of the gas is so high that gravity just takes over and it starts collapsing down onto itself. And at the very center of that is where you will get a baby star forming. And it will be surrounded by gas and dust. You know, carbon and silicates will form, kind of clumping together and make it very opaque and hard to see. But then as that material starts to gather together in the center, any residual sort of motion ends up sort of spinning up the material around it. And all of that other stuff, the carbon and the heavy elements that are starting to form that disk, they're the seeds for planets to form around that star. So, you know, basically the planets that we see in the solar system, they were sort of formed from the leftover debris that didn't make it down into the sun.
Okay, so the sun is a star, right? And it sort of, remember that video game where you'd roll along and things would stick to it? Anyway, so it's like it's like that.
Katamari? Is that the one?
That's it. That's a great, really. So essentially, it becomes dense enough that it has the power, and it's hot enough and strong enough to become a sun because of the density.
But then imagine if you're playing that game, imagine then you make that ball so big that its own gravity starts crushing it in, and you get a really dense, like burning ball in the middle, and that's what happens with the star.
I can be taught.
You know,
that's what we're
burning,
learning.
And the burning that goes on, it's not like fires. It's not like burn isn't really a good word. This is actually processes of nuclear fusion, where you get the densities are so high that the hydrogen atoms can smash together so quickly that they actually overcome their repulsion. You know, their electric charges on nuclei, and they tend to repel each other. But if you can get them close enough, this other force takes over. Something we call cleverly the strong force. They smash together and they release energy. And so that process of nuclear fusion is what generates the power that lights the star up.
Okay. We have a complicated question. Someone who knows about the James Webb Telescope. So it's Mongoose Sausage. Mongoose Sausage. Come on. Mongoose Sausage would like to know, what more will the James Webb Space Telescope be able to see, and when does it launch? Explain to me what the James Webb Telescope is, and then I've also been given a note that the launch is sometime in 2021. Anyway, but what is the James, and what do you think it'll be able to see?
So the James Webb Space Telescope, is short, JWST for short, or Webb for short, is essentially the next generation of space telescope to follow on from the Hubble Space Telescope and the Spitzer Space Telescope. So this is being launched sometime in 2021 to do a whole range of astrophysics and planetary science. It's going to really revolutionize our understanding not only of those areas, but also of exoplanets. And this is largely due to its increased sensitivity, but also the broader wavelength coverage that this telescope will have. And so basically at different wavelengths, the atmosphere will give off different, there are different fingerprints in the atmosphere that you'll be able to detect at different wavelengths. So we'll have access to a whole bunch of other gases that facilities like Hubble weren't able to access, things like other methane features or perhaps signatures due to clouds. So it's highly anticipated. us exoplanet scientists are really excited for the James Webb Space Telescope to launch, because I personally think that the observations that Webb will give us will completely revolutionize what we think we know about exoplanets and their atmospheres. You think you know, but you have no idea. What is that? That's a catchphrase from somewhere. Is that real?
Right.
Yeah.
Exactly.
So the same goes for exoplanets. I think we have a vague idea of how these planets have formed and what they're made of, but I fully anticipate that James Webb will completely, surprise us. Yeah.
Because it's got all the current tech, because every time something is launched, the engineers are making a new version, right? So the new science that will come back is it's brand new, right? New wavelengths and new levels of detection.
Right, exactly, yeah.
That's cool.
Well,
Anyway.
Tiffany's actually involved in helping design one of the next generations of telescopes that would be possibly one of the successors to the James Webb.
You guys, this is amazing. We are talking with scientists. Are you excited about it? There's more questions. Captain Gene Hammond. Do particles that move past an event horizon move faster than light? Since light cannot escape, the force of gravity is greater than the power of the speed of light. Ooh, that does sound science fiction-y. What's happening? Who can translate that for me? Robert.
This is your black hole question. No astronomy
okay.
chat is complete with at least one or two black hole questions, because they're really cool things. So I am far from a black hole expert myself, but I will say, at least I can state with confidence that at no point will anything ever actually move faster than the speed of light. It's a thing that you can strive for, but you can never achieve. And so even as weird as things happen around the event horizon of a black hole, where space-time is curved and stretched so far, just distorted so far that light itself can't escape out, particles will never ever actually exceed the speed of light. It's the laws of physics are very, very protective of that speed limit right now by everything that we've seen. So it's particles kind of go in. The more material you put into the black hole, the more it kind of deforms and the more it expands. But nothing ever actually quite exceeds the speed of light in the process.
I think you explained this to me one other time. Yes, that is disappointing. We have a fun question from the internet at Jack Flapstack. Jack Flapstack has a question, you guys. He has a burning question. On an exoplanet, would it be possible to get pancakes any fluffier than we already do on Earth? It turns out Jack Flapstack has a pancake obsession. When astronomers describe an exoplanet as habitable, what do they really mean? And then also talk to the pancake issue. Jack would like to know. What do you got?
Well, I can only hypothesize. I have to admit, I haven't seen any peer-reviewed papers on exoplanet pancakes, or exopancakes, I guess. But if you look at what happens on Earth, I am aware of the fact that if you go to altitude, your cakes tend to get flatter and your pancakes tend to get flatter because of the low pressures, something about the way that the gases are released. They pop out so quickly the cake kind of gets flat. Now, you could extrapolate that if you get fluffier pancakes at sea level than you do, say, in Denver, that if maybe you had an exoplanet that had an even denser atmosphere than Earth, that making pancakes there the bubbles might like micro bubble even more and give you an even fluffier pancake. Now, I don't think we've tried that. I guess the nice thing is this is something that we could verify experimentally. We could try to make pancakes in pressure chambers with different atmospheres, different compositions, and we could actually, in principle, do that experiment. But I don't know. I don't know, Tiffany. Do you know anyone who's looking for a good pancake exoplanet research project?
I mean, not off the top of my head, but maybe it's something I should work on. I really have a hankering for a pancake now, so thanks for that.
Could we somehow tie that into our definition of habitability to kind of bring it around to the other part of his question?
Well, when you go to a new planet, you're going to want a place to get pancakes. No? Too soon? Okay.
The interstellar house of pancakes?
pancakes intelligent life, you know? I mean, if you find an IHOP on another planet, you got to know there's intelligent life there. So,
Exactly. So Corey Palmer, by the way, Vestbinder asks on Facebook, how can we find out if exoplanets have oxygen? Is that possible yet, or?
yeah, so there are actually different techniques that we can use to find out. Ultimately, it boils down to telescopes. So telescopes actually can allow us to find out if these atmospheres have oxygen. But with oxygen, given what wavelengths those fingerprints of that molecule exist, we can actually use telescopes not only in space, but also from the ground. So these big ground-based telescope light buckets, we can also look for oxygen. And so oxygen as a molecule has different spectral properties that allow you to actually resolve the spectral line at different wavelengths. And so there are basically different techniques you can use with telescopes to try and find this particular molecule. And that's actually, I'd say, a main thrust of research right now in terms of what sorts of telescopes, what sorts of techniques we can use to find oxygen in potentially habitable planets, particularly actually around M dwarfs.
Oh, cool. There was a question that came before we started that I would love to, if you could answer. And it came from at Funny Sunny Bunny with an I. Anyway, how much, if any, detailed information on a planet's topography are you able to discern? And that, just because of the telescopes, one would imagine you would be able to get to that. So,
Well, like Tiffany said earlier, even when we do direct imaging, it's really hard. There's only a handful of planets we've done, and what we're really getting there is just a speck, a dot, an unresolved, and not actually showing surface features. However, that doesn't mean there aren't some kind of clever techniques that we can start to get at what's going on the surface. There are certain planets that we've been able to observe, some transiting exoplanets, that in addition to seeing what happens when the planet passes in front of the star and blocks some of the star's light, we can also detect when the planet passes behind the star and the star blocks the planet's light. And in fact, we can follow the overall brightness of the system over time as the planet does in orbit. And sometimes, for a few cases, we can actually see sort of rising and falling amounts of light in the system, which we call a phase curve. And what that is giving us, the beginning of like what you could call a temperature map, because usually we've done this in the infrared. So imagine, if you look at the moon and the moon goes through its phases, sometimes it's brighter, sometimes it's dimmer. You can do this by looking at orbiting exoplanets in the infrared and sort of figuring out which part of the light is coming from the exoplanet versus from the star. And then you can start to make arguments about what the temperature map for the whole planet is, that, sort of varying across latitudes. And so we actually can start to put ideas together about what planets are made of. In fact, there was a press release that just came out last week on a terrestrial exoplanet, something that was only about 30% bigger than Earth, orbiting an M dwarf star, like the ones we were talking about earlier, but it's so close to the star that we're actually seeing the light of the planet re-radiating the star's heat in the infrared. And we have mapped out the different light that's coming from the day side and the night side of that planet. And from that, we've been able to deduce a lot of things. We've been able to deduce that it has probably virtually no atmosphere, because the night side seems very cold compared to the day side. And if there were a thick atmosphere, we would expect temperature, the atmosphere would carry the heat around to the backside, but we don't see that.
Okay.
And then we also, by looking at how bright that planet is in the infrared, we can start to calculate what its surface properties must be like. And it turns out that in order for that planet to have the infrared profile we see, we think it must be basically black, like absorbing almost all the light that falls on it. And the cool thing there is there's really only one common mineral that we see, around the Earth and the solar system, something called basalts. Think sort of the lava plains in Hawaii, right? Something that's very dark, absorbs most of the light that falls on it, but re-radiates in the infrared. So here's a planet that we figured out there's no atmosphere. We figured out that its surface might well be have a lot of basalts on it. And while it's not exactly like continents and surface features, it's those first steps at getting at a little bit of that information.
Okay, that is fascinating. Okay, I'm going to do 2 more questions and then we will have to go, but we'll come back. We'll come back. You'll get to talk to more scientists. It's going to be amazing, you guys. This is very exciting. It is called, you're going to drop some things in the background, NASA Universe Unplugged live chat. So it's been very exciting for me. But here's Heather Crockett at Planet Quest. Why can't we see more detailed pictures? Well, now you might have just answered this. Detailed pictures of the exoplanet being discovered. I'm sure I'm way out of my league. If we can see other galaxies, why can't we see these other worlds in our own galaxy? So maybe Heather wants to know why we can't get better pictures of Jupiter. Am I misunderstood? Very possible. What do you guys got?
Well, Robert, actually, if you want to take this question too, if only so that you can, because this is a big challenge. So a lot of Robert's work goes into visualizing some of these exoplanets. So we have the challenge of, we can't necessarily see these high resolution pictures of an exoplanet. So what goes into, creating the pretty pictures that the visualizations for planets that you see in, say, the habitable zone. So I just want to punt it to Robert so he can talk about that.
Well, you guys are have each other's backs, and I like it. Go, Robert.
Yeah, no. It's kind of following on what I was saying before. It's really just a question of scale and the size of the telescope and the sharpness of an image from the telescope really ties to what the size of the mirror basically is in the telescope. I actually had a great opportunity just recently. I was up on Mount Wilson, looking directly through the 100-inch telescope there. A friend had a birthday party who's listening to us. Hey, Rajan. And having this 100-inch mirror looking through at Jupiter, while I could see the disk of Jupiter very well, even the moons of Jupiter, I could just barely make out had some dimension to it. And those moons of Jupiter are very close. They're takes light less than an hour to get here from Jupiter. Now, the nearest star, it takes like 4 years to get to us, right? It's so much further away that even with like the biggest telescope we can imagine building right now, you can't get enough sharpness in it to make that little speck of light that's a planet, resolve it so that you can start to see those surface features. That's one of the reasons for what we did in our series, The Habitable Zone, and we wrote it as a sci-fi show where we actually got to take a ship and actually go and visit one system after another to give us an excuse to be able to actually look at the surfaces of planets and see what conditions, and use what you see in terms of surface conditions to kind of help tell some of the science stories that we are piecing together from these indirect observations, but it's always a little more visceral to imagine what it looks like. So for the time being, I get to have a job like making artwork of what a planet might look like, just because it's going to be a long, long time before we have pictures to disprove any of the art I've done so far.
Well, fair enough. And this actually leads into the last question, which Hendrik Venter has asked, which is, can moons have moons, and can they be habitable? Tiffany? You want this?
Yeah, sure, I'll take it. So this one's an interesting. So I think maybe what he means is, can exoplanets have moons? And so the answer to that is absolutely, yeah. Even within our own solar system, right? Jupiter has tens of moons. We obviously have one of our own, and that's actually a big driver in the search for life as well. So thinking not only about exoplanets and whether or not they might be habitable, but then also, could the moons around, say, a Jupiter-sized planet be habitable? And so there are some candidate exomoons that have been searched for and potentially discovered. So a lot, and even within our own solar system, there's a lot of work understanding if Titan, which is a moon of Saturn, perhaps its atmosphere has the conditions that could, lead to life. The kind of general perspective on Titan is it seems to be somewhat of an analog for Earth early in its history, and so it might have the right ingredients for forming life. There could be there's been a lot of work on some of Jupiter's moons, Europa being one of them. So it has this icy sheet on the surface, and it's been hypothesized that there's potentially this very thick subsurface ocean. So maybe there's a whole bunch of marine life that lives there. And so those are all moons of these planets. And so, it stands to reason that these exoplanets could also have similar moons that could, have these rich environments.
Sure.
So you
And,
think Pandora from Avatar could be real?
I know that Robert Heinlein wrote "The Moon is a Harsh Mistress." You guys, my name is Jackie Cation. I'm a comic. I have a podcast. You could find me, whatever. It doesn't matter. But this is all the time we've had speaking with scientists at NASA. You could always learn more at our Universe Unplugged YouTube channel, or if you go to exoplanets.nasa.gov. Tiffany, Robert, thank you so much for taking time to explain things. It was very exciting. Thank you very much.
Thanks for having us.
Thanks, Jackie.